Hi, welcome to our next complex numbers video. We continue discussing polar form. Now we know by now that complex numbers can be written in rectangular form or polar form on an Argand diagram. We're going to now solve some equations that have complex roots using polar form. So we're going to solve z to the power of 3 is equal to 8. We could normally write it as x to the power of 3 is equal to 8, but because there's complex roots involved, we often refer to just z. All right, here's our Argand diagram, and 8 is just a number on the real line. There's no imaginary bits. So when we go and convert it to polar form, we're going to write it as 8 to 0 degrees. We'll work in degrees for this first problem. 8 has a modulus of 8, and the 0 means no rotation. Okay, let's solve it. To solve it, we get rid of the power of 3 by taking the cube root. And the cube root is exactly the same as taking it all to the power of 1/3. Now we're going to use De Moivre's theorem from here, and we're going to go 8 to the power of 1/3, and 1/3 times the argument, 1/3 times 0. Now 8 to the power of a third, I'm grabbing my calculator. 8 to the power of a third is 2, which is the same as the cube root of 8. And 1/3 times 0 is still 0. So we're left with 2 cis 0 degrees. Now 2 cis 0 is in rectangular form just 2 whole and no imaginary bits, and it's just equal to 2, a whole number of 2, because the cube root of 8 is 2. Notice I've called it Z1 because I've found my first solution. The fundamental theorem of algebra states that every polynomial equation of degree n has n roots. So because we're solving an equation of power 3, we're finding 3 solutions. And we've found the first solution, which is 2, which is a whole number, a real number, and it's not complex. But the next 2 solutions will be complex. So let's go back to our diagram, our Argand diagram, and let's plot the Z1, which is 2 and no real bits. And let's use this little trick up here. To work out k, we go 360 degrees divided by n if we're working in degrees. Now, n is 3 because there's 3 solutions. So 360 divided 3 is 120 degrees, and that's this number called k. Now, what are we going to use that for? We know the first solution, Z1, is 2 cis 0 degrees. To find our second solution, we rotate our first solution by k, by 120 degrees. We keep the same modulus, so it's going to be 2 cis 120 degrees. That's our second solution. And our third solution, we rotated another k, another 120 degrees, and we get Z3 is equal to 2 cis 240 degrees. So our first solution was a real number 2, but the other 2 solutions were complex roots in polar form. All right, let's do it all again. This time we're in radians. So w to the power of 4 is equal to 5 cis pi over 3. So let's take the fourth root of everything. That gets rid of a power of 4, and that is the same as the power of 1/4. Now let's use De Moivre's theorem and go 5 to the power of a quarter and a quarter times the argument, and that gives us 1.495 for the new modulus, rounded to 4 significant figures, and pi over 12 is the new argument. Now let's use the k trick again. This time we're in radians, so it's going to be 2 pi over n. N is going to be 4 because there's 4 solutions, and that simplifies down to pi over 2. Now, we know the first solution. So to find the second solution, all we do is take the argument of pi over 12 and add on a k, which is pi over 2. That gives us 7 pi over 12. Then we take 7 pi over 12 and add on another pi over 2, which gives us 13 pi over 12. And to get our fourth solution, we take 13 pi over 12 and add on another pi over 2, which takes us up to 19 pi over 12. And there are our 4 solutions to this problem. Now, a quick look at a visual diagram. You will see W was the original complex number, and W1, W2, W3, and W4 are all our solutions to this problem. All right. Thank you so much for listening and watching.